Right. Yeah, welcome back to the next minute here.
Okay, thanks. Yeah, so let's talk about S3, the supreme part of Canada, or simple closed curves, or special cubes.
Sorry again, it's every thought that we find a title that has two meanings. At least two. At least two.
And now the exercise is to guess what's the next. That's the last song title. It has to be 3 letters. So. Okay, so what was the point of the last lecture? The point was we can build geometry complexes quite easily. Right? All we need is this combinatorial data of a vector or space with walls, anything of the sort, and you get a geometry complex. And you also saw that you can actually do the tutorial groups, right? Or this was the upshot of the last, I don't know, 10 minutes of last time for that. Well, especially in this question where your group is hyperbolic, it's easy, it's not easy, but you have to cubulate it. And by cubulate, when I say cubulate, I mean actually properly and compactly on a cube. Okay, but we saw already that there are median spaces and heavy graphs and injective spaces. So like, that's the point. We want to get something back about groups. Right? But we really care about geometry group theory. So the talk today will be about what kind of properties we can get back about groups. And next up will be about what limitations we have to those. So here is the first definition. We say that the group V is residually finite. If the intersection of all finite inner subgroups in G is trivial, or in other words, for every non-trivial element of G, there is a finite quotient of G in which it's non-trivial. Okay, so here is an exercise. And probably all of you saw this definition. But still, let me give the following exercise. So G is residually finite if and only if G is outflow with respect to the profinite topology. Profinite topology. So what is this profinite topology? It's the topology generated by the basis of cossets of finite indexes. Okay, so the residual finiteness somehow translates into a topological property. Some nice topology one can put in a group. Okay, so this is an exercise, and here is maybe the first theorem, which will be the sort of model theorem for what's coming up later. That the free group is usually finite. Okay, so what we'll do is we'll give a proof of this that we can later generalize. Okay, so I mean one can also prove this. Yeah, so the idea is the following. We can view, let's do it for n equals 2. We can view F2 as the pi 1 of the F2 equals A and B. Okay. And we want to show that for every, to have this non-trivial element if I want to find this finite in the subgroup, find want to show. Yeah, with the finite index subgroup such that V does not belong to it. I think this is exactly what. Okay. Yeah, so let's maybe think of an example to illustrate what's happening. So maybe G is some word. You copy that and whatever, a word. A, B, A squared, B. Okay. So the first thing we'll do is you'll realize this word as a path that is sent into this flow. So I can do A and then B and then A squared and then B inverse. Okay, so I have this path that maps into this rows. And the image of this path would be a code representing G in the path. And the trick would be turn this path somehow into a finite cover of this path. So embed this path in a finite cover of the rows. Okay, if we manage to do this, then if we declare this to be the point in which we compute the phi one, you see that this element, since it's embedded, is not a loop. It does not belong to this finite index. And there's sort of like a canonical nice way of doing it. So what's the nice way of doing it is, well, you have to fix the fact that it's not a cover. So what does it mean? It's not a cover for each vertex. I'm expecting to see an incoming and outgoing A, incoming and outgoing B, and so on, but it's beyond the maybe part of it. Okay, so what you do is you add those edges. So here's the canonical way of doing this. You look, for instance, at A, and you look for a maximal subpath on which you only read A. Okay, so this ends with an incoming A and starts with an outgoing A, in which they're missing things, right? So what I can do is I can just close it up. This will be one thing. And there's another path of length 2. Again, close it up. Yeah, same for B. Am I done? Not quite, right? Did I miss? Yeah, thanks. Right here, I'm missing an in here and not my B. I'm missing something, an A maybe. Yeah. And the point is what we created here is now a finite cover of the rows in which the element of B is not a row.
Yeah.
Sorry?
One more V loop in the middle.
Ah, excellent. So V is not in the pi one of this line. With this point. And this is this finite index of my pi one there. Yeah. Let's say that, yeah, simple. And I'll say that this type of proofs is really what pushed me to go into books. I saw this like it's no better math than this. Okay, so here is the upgrade of this thing. That's a theorem of Marshall one. Any finely generated subgroup of the free group is maybe I need a definition before. I mean, the theorem, okay. Erase it. Put the theorem back. And going to generate some group is the definition. Subgroup H of T is separable. If you can separate every element of G from H using a finite unit subgroup, and for every G not in it, there exists a finite unit subgroup. Such that G is not in. Okay, so one residual finiteness is the same as the separability of the theory.
You have to contain each.
Right?
You can contain each.
Thanks. Yeah. So the remark is one is separable. You can only G is finite. And maybe another exercise is similar to this. H is separable. You can only H is closed. It's closed subgroup. Again, with respect to the cosine. So for a group topology, the house of it would be the same as saying that the points are so. Okay, so the theorem is for every finite generated subgroup of the free group, we know that it must be separable. In fact, what we will show, and this is the theorem is that if H is virtually, and I explain what it means in that way, virtually free five. Okay, and here is the any substance to do that.
I have a very general question.
Yeah.
So we don't know about groups are residual finite. Do we know of separable subgroups in groups? Like
What's the question?
if I had to like are there certain subgroups that are not to be separable in any inequality? Sorry,
It's not like we're asking for something more than
yeah. Okay, yeah, that's my thought.
what is sorry? What is the frequency? Yeah, I'll when I get to the side. That's it. But we know what the problem is. So let's go. And we'll see what the proof actually gives and then we'll be clear. And yeah, okay, so yeah, so what's the proof again? You want to think of the single as find one yeah, and the next step is you want to think of H as it's a map from a finite graph into the field. So the way to do this is the following. So yeah, so you can think of H as what's called the size for H. So what is that? You look at how H acts on the universal structure of this guy. And inside this thing, there is a minimal invariant subtree. Minimal invariant subtree. That's what Q of H. So this, for instance, use what Atelier called us This one more basic than that. Okay, and in fact, it's unique if H is not true. Great, and what we can do is we can look at the core. So the core would be just take P of H mod V. So, okay, I hope you can realize I'm lying a bit, right? That's the core after conjugation. Great. Yeah. So this is something you can actually compute. Start with the generators. Start with the generators of H. So let's say H is generated by some elements and AB squared and something else. AB, B. You write them in such a way. So AB, AB, and AB squared. And to form the core, this graph, what you have to do is you sort of have to make this map from this graph into this rows into a localization. So the labels here tell you how to map each head to this rows, and it might be that this is not the localization. For instance, on this vertex, I see two edges labeled A coming up. Okay, this is the case. What you could do is you could fold them, make them into one edge labeled. Yeah, so this is folding. So you can actually compute this thing. That's the main thing. But what's really important for us is that this core satisfies that. So let's give it a name. So gamma has this nice embedding into not embedding, sorry, localization into the rows. The image in Taiwan. So let's just do maybe an example. We can try and do this. After you fall, okay, you know, people see falling before. No, see. Do it here and not embarrassing. Yeah. So I'm just going to write some example of such a graph. So here and here maybe another. Okay. So again, really the property that I care about is the fact that this is the localization. So each vertex here, I see the most one incoming, outgoing A, B. Okay. Great. So yeah, our goal is to say that this is separable. So one way of going about it is trying to sort of mimic this. Take an element that's not in H, right? This would correspond to some path that path in here, or maybe a path that can go outside this and try and do the same, say the same thing. But actually, there's an easier trick here. So the easier trick is to just do this like canonical completion of this stuff gamma into a cover. Let's draw in Nazi yellow. Again, I'm doing exactly the same thing. So I'm following paths of A and B and closing them up. Okay, so here's the path of A, close it back. Okay. And here's the path of B, close up. And maybe I'm done. We're done. Who found the good. Right, so we have this finite, this is the finite thing like subgroup now of my tree. And here's the nice thing, it comes with a refraction. So there's a refraction going from gamma back to gamma. So what is this refraction? Every edge I added, I can just map to the path that it closed. So this I would map back to the A squared path. Okay, and this guy I'll map to the B squared. Okay, so this gives me a refraction from C gamma to gamma, which in turn gives me a refraction from the final one C gamma into final one gamma. Okay, so this guy was my H, and this guy is some finite index subgroup like the first one to zero. I get this map from the finite index subgroup of the H, which is very fine. And here's the fact, or the exercise, the next exercise. Every retract in a also space is closed. If the retract and X in household, it's closed. It will be topological statement. But in our case, what do I get? I get that H is a retract of maybe, okay, a finite index subgroup. So we any finite index subgroup is closed. It's Hausdorff. Why is it Hausdorff? Yeah, Hausdorff 5 exercise. H is a retract of K. Okay. K is Hausdorff. Why? Yeah. Okay, I bored you. I see. It's really fine. Right? That's the previous thing. Okay, and so H is closed. Being closed is the same as being circular. So really. And yeah. So actually what we got here is that I think we got even more. The fact that H is literally a free factor. So free factor, yeah, is H is has a free subgroup complement. So I can find some A, so that this is in this situation, I'll say that H is a free factor.
Where did so the part of the diagram that it's in white, where did that part come from? Yeah, how was that
Part of
constructed?
the diagram that's white, this is the
Yeah.
core. Okay, so there is some graph that locally embeds into my tree group that carries all the fundamental group of my second H. That's the point where I use the fact that H was finitely generated. And so free factor means you can write something like this. So there exists an A that completes into the decomposition. And virtually means, well, it doesn't do it for my group G, the free group, but to a finite index subgroup. And this is exactly what we got here. So we got this finite index subgroup K, and in fact, being a subgraph of the cover of K means you're in fact a P. So this is what we want to generalize. And part of the free group. So the goal is prove the same for cubulated groups. So we want to show that there is a group. We want to show that all finite infinity but okay, this is the problematic goal. It's not true. Okay, so the whole point of the next lecture is to show that. So this is lecture number 4. There exists non-residually finite, cubulated In fact, there exists simple. Not only that they don't have enough finite quotients, they just don't have any proper captions. So simple. Okay, so yeah, that's out. But we can play the game. We can try and play this game, decide whether it works or not. And this is really the brilliant idea of Haglund and Wise is to find a good subclass of related group for which we can play this game. So that's really where we are heading. Yeah, so before I introduce this class of group, I have to begin the lesson. I'm going about it. The workshops. Let's just try and play the same game, but now our target space will not be the hotel here. That's a like. So let gamma be the complex. Okay, so let me remind you what this is. So gamma will be some finite graph. So let's just take an example. Okay, and then the Helvetic complex. So the Helvetic complex would be the cube complex you get by taking one vertex, okay, touching an edge for each one of the generators. And whenever I have two vertices connected by an edge, I'll put torus, the blue, this guy, into the top. I'll get the torus connected. And of course, if you have fleets of higher fleets into cubes, you can use it again, but focus on the second. Right. Yeah, so just remind you that phi one of this guy is the right angle Gaussian group corresponding to gamma, group generated by the vertices with commutation relation captured by that. Okay. And now let's play the same game. So instead of starting with the finely generated group or I'll just start already with something I can play with, which is this. Okay, so let's say I have Y is some non-positively curved cube complex with a local isometric embedding into S. So this would be a local isometric embedding. Yeah, so when I say this, maybe I should say something. I mean local isometric embedding with respect to the ket geometry. Okay. So let's just maybe play with this a bit to see if you understand it. Yeah, so for instance, you take the following graph. The following non-positively curved complex, maybe this is my Y. Is this conversion into here a local isometric embedding? Not too much forward. So what do you think? Squeezing, how much staying? Uri? Huh?
I think it's okay.
It's okay, okay. Uri can still. Any other opinion? Yeah, so I mean the thing is it's not okay. It's good to have Uri. Yeah. why is it not here? So, I mean, the distance between those 2 points, right, in y is going like this. So it's whatever this is plus this. While in S gamma, between the pink and the green edges, I have a square, right? I have a 90-degree angle. So actually, in gamma, this will be shorter. Okay, so this is not a localized matrix. So what we see is that for this to be kind of a localized matrix embedding, whenever I see things that commute beyond there, they have to sort of carry on going, right? So this is fine.
We think so.
Right?
We think so.
It's right. Also, okay, yeah. We think so. This fine. The same thing.
No, that's good. That's the other.
The bubbles are. This is fine, right? Because locally the yellow is not connected with the straight line. This is fine. And they do something more crazy. That's something like this. That's fine, right? Good, I understand. Something like last one.
Oh, sorry.
Yeah. Something like this. So, done the same thing so far. Okay, then my third. Okay, so here I see an angle. By the way, when I draw those things, I should really be drawing arrows. You imagine the arrows in all spaces.
So nice, display bravery, masking so, but what about like near the end of the yellow one, like, cause it's distance to pink or green, if you have to go through the yellow there, and over there you don't. So like if you're over there.
Yeah.
Like it's distance to anything pink or green, in that one, you have to go through the whole yellow, whereas over there you can just.
Yeah, but no, I'm only asking for localized matrix. So when I do that, I only need to look at the small epsilon ball around this point and see what happens to this. And for this guy, just send this. Automatic embedding, yeah, just embedding. We're all happy?
Yeah, like you said, again, why you couldn't have the pink edge going?
The previous problematic example,
Yeah,
this thing, so just this.
Yeah.
So by the way, I can have two, this is fine. It's only when I introduce this square that things. Okay. Yeah, the reason is in S gamma, what I'm expecting to see is something that looks like this locally around and maybe the yellow, also the yellow. Right? The distance between those 2 points in this picture is, let's say, like this 1/10, 10/10, 2/10, and here it's oh shit. Just square root. And great. So this is the kind of non-positive curve spaces that I look at, those that would have local isometric embedding into my S gamma, and maybe I should say that the phi one of y. What do I know about it? Well, it must embed in the phi one of S gamma, which is this way. Why is that? That's one of the exercises I gave in the first lecture. If you have a local isometric embedding, maybe it was between Catillo spaces, then it was also this, whatever. Various version of the same thing, but right. So the phi one of y actually lives inside this inside this group. And okay, and we said what we want to do. We want to play the same game. So yeah, how do you play the same game? You take y and you consider the economical completion of y. So what did you do last time? Every time you had a path, you close it, you do the same. Okay, have a yellow path, you close it, maybe I should, try to do it in a. Everyone copy this drawing. Is it? I know it's a big cover. It's eating a cover.
Dotted lines, same color.
Sorry,
Dotted lines,
dotted line.
same color.
Yeah, it's gonna get quite nasty. This is my. No, there is. But I have also different shades of green and green. I don't think it's. Okay, here's the thing. We have the time axis to differentiate this picture and the one that will be. So I'm closing every time. Know that I have many other yellow paths which are making the picture, right? So you're maybe gonna one. Did I miss anything? Yes. Good. Now. Good. Move on to the next color. Do the same for these. And this is fine. Here. What did I miss? Am I fine? Good. Next green. Okay. Am I done? No, it's not a cover, right? I mean, we only took care of the one skeleton. Huh? And now it's what we're going to do. Put on the squares. Okay, so we do that. Well, okay, I mean, maybe it's not immediate to see that one can actually put it on the squares, but I mean, here what you'll get is the torus, will be a torus when I put the squares in, same for here. And we just do one, but there's how to share. Yeah, so we got this space. What do we know about the space? So EY is now a cover of S graph. So finite cover. Okay. And maybe as an exercise, just to see maybe an idea of like why you can do this. And really what we're doing is we're filling in the squares that correspond to things that map into the torus point. What we really want to understand is what are locally isometric embedded complexes that embed into a S of a clique. So what are locally isometrically embed into, I want to say S of a clique, which is just the torus, right? With the standard. So this is great thing. Great, that's a great start. You have the finite cover. What else do you need? One, the refraction, and this is the second part of that. And again, you can play the same game. So everything you add, everything to the feedback. It comes with the refraction. So maybe I should say there's y embeds in the canonical completion, and there is a refraction. Okay, so when we're in this situation, we know that y is a virtual refactor of S gamma. What we wanted, so you can play this game for the. I mean, what am I missing in the truth? I want to say it's I'm missing the fact that S gamma is the visual defined. But okay, we can play again the same game, or we can use the fact that vags are linear. So we are stamping the squares. So vags the linear. And this is because the embedding might be the cluster loop, which will not be linear. And this is the y's and y and copy and save this. Only this letter or an accent or something, sorry. Great. So yeah, so we can play this game for the Salvetti complex, but we want more than just, well, okay, bunch of examples. And here's where Hagun and Maurice come in with the right definition. So this is Hagun and Maurice. It's a definition of special cube complex. So X and a non-positively curved cube complex is special if exactly X as a local isometric embedding to some. Okay, so really when I say special, I mean compact. You know, it's controversial. Let's stick to compact things because they're nicer. Okay. So this is, and why is it so special? Because we can again play this game. See how you play this game. So maybe as the first observation, since we wrote it, well, I1 of X is a subgroup of a reg, but that's like an immediate corollary, right? And so it's also residually finite because it's linear. Yeah, I didn't say. I said they're linear, but the linear groups are residually finite. Okay, this we just get for free from this definition, but actually we get more. So what we get that if here's the if y locally isometrically embeds in X is special, then well phi1 of y is a subgroup of phi1 of X again, but the point is this is separable. In fact, again, it's a virtual data. So we worked hard to do it for the Salvetti complex. So I have y going into X. X is special, so as this local isometric embedding into a Salvetti complex. Okay. But now, so what do I get? I get the y as a local isometric embedding into a Salvetti complex. So it has a completion with the finite coverage with an embedding here and the retraction. That's the one. Okay, but this is not what we wanted. We didn't want a retract of it. So that's complex. We wanted everything from X. So actually, just from this we can really get separability because X would be separable, so it's closed, and Y is closed in the big thing contained in closed. But so you can actually get this. It's not virtual retraction. Okay, you also get. But still, you can play the same game. How do you play the same game? Well, there's an object here that is above those. That's what corresponds to the intersection. So the thing here is the fiber product. So here I'll have also that y embeds into the thing because we all know what the fiber product is. We should say we don't. So that's the opposite. Yeah. And it's a subset of the product of x and cy of all points that projects all points that here have the same image, such that give those names u iota iota of x is q of 1. And this is itself a cube complex. It's a non-positive recurrent complex. In fact, it's a cover of x. So it can cover, and one can lift the map from y to here. Why? Because I have a map from y to x and to cy. Commute, so you get the map. So, but yeah, so you see, I mean, what I basically said here is that if you already know that you're in a Salvetti complex, then you can play this game. It didn't quite improve my situation. But here is where it's really nice. You can actually detect that something is a special cube complex just by looking at its hyper. That's maybe version 2 of this definition. Let's call this maybe version 1. Yeah. And so really, like, how can you tell that x special? So you check the column. And so x not positively for Q complex is special. If the hyperplanes x are first of all embedded. Remember that if x was a careful effect, you knew that hyperplanes are embedded, but if it's an NPC, they're not necessarily embedded. So the picture here to have in mind is I have a sort of chain of squares that and the sector somehow, then the hyperplane here is not embedded. So this is not good. Next game. One hyperplane to be two-sided. Again, if x is cat 0, we know that they're two-sided, but could be that when number of the recurve them. So which is here, we draw that and then use again. Note that this is sort of relatively easy to fix, right? If I have such a thing, I can just declare each cube to be each square to be 4 squares, right? Cubical is going to take something here. This will get rid of this column, but together with the next one, you're able to see. So the next one is I don't want it to self-oscillate. No self-oscillation. What's the picture here? So I don't want the hydroplanes to go back and touch itself. And remember that the hydroplanes are now embedded and two-sided. Okay, so when I draw a hydroplane, so the hydroplane is two-sided, but I can follow a side. And what I don't want to see is I don't want to see a vertex. Such that the hyperplane passes through two incident edges, getting the opposite. And so this is that. So we just remark that this is fine. Oh my God. So you see here the hyperplane is facing right, and last condition is no inter-oscillation. Meaning no intersection and oscillation. So this is the condition about two hyperplanes. Here. So I don't want them to cross somewhere. And then touch in whatever way. Really a condition though. They have to decide. Are we crossing or are we adjusting? We can change their mind. Okay. And the point is, it's not just, I mean, I think it's called by the same name, it's really finding the same object. Let's see that. So, yeah, so version 1 implies version 2. Maybe this is mostly an exercise, but really the exercise here is to show that the Salvetti complex is fine, has all those properties, and that whenever you have a localized geometric embedding, this preserves those properties. Exercise is grammar better. Plus better. And is preserved. Under localized embedding. You understand what I mean, right? Full practice. And going from this to that, well, here there's this mystery gamma, right, that we have to find. And sort of a natural way of describing gamma. So gamma, so take gamma to do just the collection of hyperplanes. Hyperplanes of X. And you put an edge to each of the vertices. You put an edge to the cross. And really what all of those things are supposed to tell us is, so it's important to see that, they cross, they only cross, they also, maybe this is bad, but I mean, really what all those things tell us is that the obvious map, right, so if I extend the vertex of my non-positive vector complex, and I want to define our map to S of gamma, what do I do? Well, I map all the vertices to the one vertex I have in S gamma. Okay? They don't have no place there. And for every edge, there is a dual hyperplane. And what I should do is I should send it to the edge corresponding to this vertex in gamma, which is the hyperplane. And really all of those things are supposed to tell us this is well defined and it's local. That's the obvious map from X to here. Is the localization. Okay, so now you can take your non-positively curved cube complex from the gutter, and check if it's special. If it is special, you get also nice properties like being very finite, being linear, having certain separable subgroups. And maybe another remark is that separability is really strongly related to being special. So maybe the definition version 3 is that you're special, but special if hyperplane stabilizers are separable and also product of two hyperplane stabilizers is also separate. So in a sense, this is sort of an if and only. Okay. So where can we use this? So here is one way we can use this. So if X is special, maybe no, I don't think that. Let just be a non-positive curve cube complex. And Y yeah. I was thinking it's going on too. Oh. Okay. Thank you.
Any quick questions for you? Any long questions for you?
So it's very good.